All right, everybody, welcome back to the last edition of our talk about spherical coordinates, although they are not going anywhere for the rest of the term. So let's talk about maybe some spherical non-boxes now, and let's start by talking about some equations of spheres that are not centered at the origin. In particular, let's see, pick your favorite number A, and let x squared plus y squared plus z minus a all squared equals to a squared be the sphere of a radius a whose center is 0, 0, a. Okay. Then if we multiply out what is this z minus a squared, then we can write the whole expression as x squared plus y squared plus z squared minus 2az plus a squared equals to a squared. And notice here we've included the picture for your convenience that this one is centered at the point 0, 0, a and has radius a, so it grazes right against the origin there at the bottom. And so we can take this equation that we have and cancel the a squareds from both sides and bring over 2az to the right. And we have this nicer looking expression, x squared plus y squared plus z squared equals 2 times a times z. Okay, well, we know how to convert this now to spherical coordinates because I know x squared plus y squared plus z squared should be rho squared, and 2az should be 2a times rho cosine of phi. So, and so, okay. So we have, in fact, rho squared equals 2a times rho cosine phi. And in fact, okay, so what I showed here was a little bit extra step that is not totally necessary because we really know x squared plus y squared plus z squared is rho squared. So we have here rho squared is 2a times rho times cosine of phi. We can cancel the rho's if we're assuming rho is not 0. There's only one place here where rho is 0, and it's that point at the origin. Hopefully, we'll be able to get that back from what remains of this equation when we divide out rho. Namely, rho equals to 2a times cosine of phi. This should remind you of something from our polar coordinate conversation. Those circles in polar coordinates that had the form r equals to number times cosine of theta, or r equals to number times sine of theta. Those circles that were offset by some amount but still grazed against the origin. This is just the spherical coordinate analog of that. Okay, so let's see. So this looks like another good equation to have, so we'll just record that here as a sort of fun fact. The sphere of radius a with center 0, 0, a has the equation rho equals to 2a times cosine of phi in spherical coordinates. Okay, so maybe let's use that now for some good. This next example says, let E be the region of space that lies above the cone phi equals to pi over 3. And below the sphere, rho equals to 8 cosine of phi. So let's see, maybe you stop and think, what is going to be the radius of this sphere? I think it should be 4, right? Because we have here, this would be 2 times a. A would be 4 in this case. And so it'll be centered at 0, 0, 4 as well. So here's a picture of that sphere, but I've chopped it off along the lines that come from the cone phi equals to pi over 3. So this region that lies above that cone but below that sphere, that's another way you might say that is that this region E is bounded below by the cone phi equals pi over 3 and bounded above by the sphere rho equals 8 cosine of phi. So it's this kind of funny looking region. Okay, so it looks kind of similar to the spherical box that we saw at the end of the last video, but maybe it's a little bit different. It looks like, what's our upper bound going to be for rho? Well, it looks like we start at rho equals to 0. And let's see, for phi equals to 0, we have along the z-axis here, rho goes from the origin, 0, to 8 cosine of phi. And as we keep moving along phi-wise, let phi increase, our radii rho still go from 0 out to 8 cosine of phi. So it actually looks like even when phi is this end part, phi equals pi over 3, the radii still start at rho equals 0 and go out to this sphere, rho equals to 8 cosine of phi. So I believe this will be maybe our upper bound for rho across the whole region, and our lower bound for rho will be 0. What about theta? Well, once again, it looks like the shape that we have here wraps all the way around the z-axis, so the thetas vary from 0 to 2 pi. They go all the way around. I guess I haven't shown you an example where theta doesn't vary from 0 to 2 pi. So I don't know, maybe we might think about that. Maybe if we wanted the part of this region that just lives in, say, the first octant of space, then maybe we'd let theta go from 0 to 2 pi, right? So we have chop out just this kind of first octant part. Yeah, we could talk about some more examples like that maybe when we meet for class time, or maybe hopefully when you get to your homework, although I don't know what kind of variety WebAssign is giving there. So we'll just have to see. But for now, let's see. It looks like, I know students like to ask, like, does theta always vary from 0 to 2 pi? Well, not technically, but it seems like all the examples that we ever get look like these really nice regions where, yes, theta varies between 0 and 2 pi. It goes all the way around in the sort of xy plane direction. So, all right, and so here's that alternate description, just changing the terminology. So we've got here that E is the set of rho theta phi, where rho goes between 0 and 8 cosine phi. Theta goes between 0 and 2 pi. And phi starts at 0, right, at the positive z-axis, and ends at pi over 3. Okay, so this one's almost a spherical box, except for this one bound here that is a function of phi. So that's the integral that we'll do first then, that rho integral, since one of its bounds is actually a function. And so the volume of E is then given by this integral from 0 to 2 pi of the integral from 0 to pi over 3 of the integral from 0 to 8 cosine phi of the function 1, which is what we integrate to get volume, times that spherical Jacobian matrix determinant, rho squared sine of phi. And we'll do the rho integral first, the phi integral second, and the theta integral last. So let's see what we get. The rho integral looks like it's just 1/3 rho cubed. So then we have, we'll evaluate that guy at 8 cosine of phi and at 0 and take the difference. And it looks like we get 8 cubed is 512. So we'll get 512 over 3 times this nice double integral of cosine cubed of phi times sine of phi d phi d theta. Okay, so I think this one is probably screaming out to us that it is u substitution, right? Don't we want to let u be cosine of phi? So then du will be negative sine of phi d phi. And let's see what's going on. If we want to change the u close, we've got to change the bounds, right? And so u of 0 is cosine of 0, which is 1. And u of pi over 3 is cosine of pi over 3, which is 1/2. Okay, so then let's dress this integral and the u close. So it becomes 512 over 3 times the integral from 0 to 2 pi of the integral from 1 to 1/2 of negative u cubed du d theta. But you know, we don't integrate backwards like this, and we don't like all these minus signs floating around. So luckily, these sort of two wrongs make a right, and we can just reverse the order of integration and forget that minus sign. So then let's do this u integral. We have the integral of u cubed becomes 1/4 u to the 4th, which we'll evaluate at 1 and at 1/2. So we get 1/4 times the difference, 1 minus 1 over 16. That gives us what, 15 over 16? And if we simplify that, that gives us what, 15 over 64. So then we'll have 512 over 3 times the integral from 0 to 2 pi of 15 over 64 with respect to theta. So there's no thetas here, so we'll just slap a theta on and multiply by 2 pi. And so what do we get is 512 over 3 times 15 over 64 times 2 pi, which simplifies to 80 pi. All right, so that was a pretty good example of us integrating over a spherical non-box. Um, and so I don't know how much more difficult the spherical non-boxes they ask us to engage with really get. But if they get any more difficult, we could talk about those in class time or via email or some other avenue, hopefully. So I think this about concludes it for chapter 15, too. So join us next time and we'll move on to the last chapter in this course, chapter 16, which is a great one. It brings everything together that we've learned all semester. So don't miss that.